I want to start out with kind of a caveat, and that is, if you really are serious about doing dense matrix math or linear algebra, you should probably still be using MPI and something like Scala Pack, right? The distributed linear algebra package developed by Jack Dongara and many other very brilliant people. They've had a big head start. Now, the thesis that I want to convince you of here when you come out of this is that Spark, I think, was designed for sort of data-driven shuffles, and not so much for algorithmic-driven shuffles, where we know exactly how to predict the kind of data dependencies that are going to rise based on the algorithm itself. And so when we switch into that gear, using the old shuffle that we've heard so much about, it turns out to be a little bit suboptimal. So I'm going to show you this Flyby. It's kind of a naive algorithm, but there are certainly ways that we can improve this into being something that's worthy of the infrastructure of Spark. So let me start out with, let me make sure my clicker works. Okay, great. Okay, I'm going to tell you, first of all, the matching use case that got me going on this problem. I'll present to you 3 algorithms that are kind of specific for dense matrix math. And then finally, I'll show you the evaluation. And the reason I chose to focus on the dense matrix problem rather than, say, the matching problem or anything else is because I really want to get down to the task dependencies that we're dealing with here. And I think we can all agree that the dense matrix problem is foundational. And we can develop random data to go feed into it. And so it's something that you can all test. And so when I show you where my code is, you can all go try it out yourself. And I don't have to make any claims about data that you may or may not have or may not be able to get. But let me start out just with a brief overview of the matching problem. This one has come up in my research and development group more than once in the last, say, year and a half or so. And so with apologies to Netflix, let's say we have users and movies, and rather than saying we're going to try to come up with, say, an implicit or latent variable model to model what users like, we're just going to assume we know what users like. We have some function f that is an affinity function for a user in a movie, and we have side information about all these things. It's something that's objective. It's nothing to do with what users want or should want. So in that case, our task really is to just apply this f to a lot of data, right? We have many users, many movies, and we just need to apply f a bunch of times, maybe a costly function. So, of course, Spark has support for that as part of the RDD primitive, and that would be, you'd say, users, Cartesian movies, map, and then you'd apply your affinity function f, and then you'd probably want to do some kind of combined by key operation because, well, the whole matrix is useful. We're probably only interested in a few elements of it, but unfortunately, we have to compute them all in order to get at that. Now, again, with a caveat, don't try this at home always because it's very expensive, and if you have, at scale, many, millions of users and millions of movies, we'll all be dead by the time that computation finishes up. But there are some times when you might have to do it. And that comes when you're developing F, right? If you go kind of with an old-fashioned approach and you get experts in there and they say, here's what the features you should look at are, and here's some data that we've graded for you, you can create that function fairly cheaply by standard machine learning methods, nothing distributed there. But you might want to apply it to a large data set and see how it performs or look at the outliers of the affinity and things like that. And then you need to do something like this. So matrix multiplication, I claim, is almost exactly the same process, right? So before I talk about that, right, we can't really talk about matrix multiplication unless we talk about how we block the data off, right? Should we decompose by blocks, tile the matrices into blocks, or should we do it by columns or by rows? So many options. But those things are sort of driven by the primitives available to us. So if we're going to do it with the Cartesian approach, because that's just what I was talking about for matching, we're kind of stuck with one decomposition. We can either do a row or a column decomposition for the left-hand argument for, let's say, matrix A. And then we pretty much are stuck with a column decomposition for matrix B, the right argument of the multiplication. And then C, of course, I'll talk about how the blocking of that works out in just a moment. But let me dig into what is going on under the hood in Spark. So the Spark Cartesian works by basically creating a new partition for every single partition, a new partition for every possible pair of partitions, with one element from A and with one element from B. It's a Cartesian product. That's why they named it that. So in this diagram here, we can pretend A and B, the labels of the rows and columns are actually like column vectors themselves, or are blocks of column vectors, but partitions in Spark. it's just a kind of a generalization, but the actual operations that go on are going to be exactly the same. And so what we see here is, yes, so for every row of A and every column of B, we're going to make a small block in our product matrix, and that's going to be a partition of data. And so if we assume square matrices, just for the sake of simplicity, we would have n partitions in A, n partitions in B, and we would wind up with n squared partitions in our product. Now, if your matrices are n by n really square, that's probably okay, because the driver has to supervise the completion of all of those partitions when they get computed. And so the driver is going to have to do n squared work, O of n squared work, to supervise all those. But each executor, let's say we have roughly O of n of those, is going to have to do n times n work. So the task is roughly balanced between what the executors have to do and what the driver has to do. Were we to change the problem a little bit, so for somehow like the matrix A is very tall and thin and matrix B is very short and fat, now we'd have an imbalance. The driver has to do a lot more than the executors do. But to review, I guess, before I move on from this slide, right, we would have each executor would have to hold roughly O of n data, one row or one column, and then they'd have to do roughly O of n squared work in order to compute out like a row or a column of that product matrix C. The next, I should at this point now talk a little bit more about other Spark internals, and that is there are many dependencies between RDDs, right? So when you create an RDD, you're either going to read it off HDFS or you're going to create it as some kind of an operation off of another RDD. And there are those like the provenance of the RDD is encoded within the RDD, and that's what allows fault tolerance and allows those to be recomputed. And there are several ways that those can be captured. They offer a like a range dependency, which allows you to take a union or a small subset of the partitions of an RDD. There's a narrow dependency, which is exactly what the Cartesian is going to use here, right? We just create a narrow dependency based on like the row of A and the column of B, and that defines the narrow dependencies of a particular block of the result. And then there's kind of the kludgeon, which is the shuffle dependency, and that, as you heard in the last talk, reduce by key, group by key, not reduce by key, group by key, co-group, join, tons of operations use that shuffle. But anytime you want to basically have two pieces of data that land in the same place based on some kind of key, that's the shuffle. And as the last speaker indicated, it requires writing to disk, and it requires a synchronization point in your code execution. Basically, all the executors have to write their blocks, check those in with the driver, and then the fetch can proceed, and those all get transferred over to disk on the destination and then read off, and away things go. So the shuffle has been highly optimized because it's sort of become the choke point in a lot of algorithms, but we can also use that to do a matrix multiplication here. So this is what I call shuffle multiply. I've got a kind of a schema of the key twiddling that needs to happen in order to make this work. So on the left column that I've got over on the right side, so there's the ij, that's essentially a block of your matrix A, and then there's kj, that you can imagine that as a block of your matrix B. And then we're basically going to do a flat map in that first stage, and what we're going to do is explode the data. And we're going to basically create like a number of copies of these blocks. Once we've created these copies, then we do the join. The data basically will land in the right place because we've been clever and set a partitioner. And then what we can do is we can do the multiplication of each of those blocks, and then we finally add up each of those blocks, kind of reduced by key under plus, but it's all local at this point. And then finally we get our block ik of the product matrix. Now this, before, for the Cartesian, I think I said that we had, each executor had to hold roughly O of n data and do roughly O of n squared work. We're a little better here. So we can throw more workers at the problem, and that means, in principle, that means we get sort of better amortization of the fixed overhead cost, basically the parallel overhead. So we can use O of n with the 1.5 workers. They'll each do O of n to the 1.5 work before we're doing n squared work. And actually, there's a little bit less data that has to go over the wire than the amount of work they have to do. So as our problems get bigger and bigger, the amount of time they spend shuffling would, as a proportion of the total wall clock time, be less and less, which is a great property. Now, what I'd like to do to improve on this is first of all, right, at this flat map step, at the second, in the diagram, right, we're exploding the data. We're basically going to create a number of copies, roughly O of n to the 1.25 copies of our data that is being held, n to the 1.75. Roughly O of n copies of the data that's being held on each executor. You know, for just to pass it into the shuffle, right? It's not like we're doing anything fancy to it, we're just copying it. And then once, I'd also like to be able to, once we've got those all replicated, I'd like to be able to avoid writing those to disk when we shuffle. So I think if I could do those two things, I could make a much faster algorithm. So that's what I call a flyby, and I think you could think of this as extreme map-side join. I'll make an example or an analogy. So back in the old days when governments, rather than trying to steal each other's data, actually just went straight for the jugular and went for sort of apocalyptic-style annihilation. And the problem arose back then where they said, well, suppose there's a couple of successful rounds of apocalyptic annihilation. How are we going to coordinate the survivors in this sort of, you know, Mad Max kind of wasteland to go continue using their precious resources to keep killing each other? So they came up with a brilliant idea, and they said, you know, we can take one of these missiles. We've got a lot of them. We'll just put a radio transmitter on the thing instead of a warhead. And then headquarters can send out the command. It'll be a one-way deal, and that thing will fly all the way across the country. It'll beam out the messages that need to go. And these surviving remnants can regroup and hopefully have one more go at it. So, I mean, this is a terrible story, and there's a lot of moralizing to do on this, but the moral I just want you to take away is relatively minor, and that is that kind of extreme broadcasting situations can be successful. So here's how the flyby will work. And so what you want to imagine is the computation cascading down from top to bottom, roughly, and we have sort of two RDDs again, left and right. And basically, the computation is going to follow or be paired with the right RDD, and left is going to be the one that flies. So this is kind of like that little transmitter that gets flown across the country and sends out very important information that the right RDD really has no access to otherwise, right? It can't coordinate with its neighbors because each partition is sort of isolated. And so what we have to do is we think of this as like an aggregation or a fold, and we specify two functions. One is a fold initialization, or F0, and one is the real fold function. And at each step, right, the left partition, L1, gets flown across. R1, in this case, will apply fold 0 at the first step, and it'll get some accumulator variable. And then we move to the next step of the computation where L2 comes in overhead, so to speak, and we apply now L2, the thing we just got, R1, the data we always had, and then the result of the previous step, the accumulator variable. And we can just keep doing this. It works all the way to the left, and all the way, it goes off the screen to the bottom side too. And now to express a matrix multiplication with this scheme, right, we would once again use it's very similar to Cartesian. We can use either a row or column decomposition. I've depicted row decomposition of A, and a column decomposition of B. At the first step, we would do A1 dot BI, whatever column we're in. At the second step, we would do A2. I think I have I have that one there. And we just keep going on like this, and eventually we would fill in the entire column of each matrix that we want to have. So let me actually show you the code here. I call this a hack because I certainly wouldn't recommend this for inclusion in Spark, but it's something that any of you could use, and it's worked very well for me. I'll show you real examples of this in a moment. The key here, though, is we basically at this line 3, we have this kind of function, get partitions as local array. So we get kind of an iterator of each partition that brings it into the driver as a local array. For each of those, we just iterate through this. We create a broadcast variable, send it out. Of course, we're relying very heavily on Spark's broadcast mechanism, which is by default kind of a BitTorrent style. It's very efficient. And we either apply fold 0 or fold, depending on what's happened in the previous steps. We persist the result, we have to count it, we have to materialize it, and then we free up the previous, the things in this algorithm that are unneeded. And I will show you in a moment that it works very well, but let's talk through other issues such as fault tolerance, right? I mean, just because we're overwriting the reduction RDD, they're defined at the second line, of course, we aren't freeing that. It remains as, with all the provenance information and necessary things to recompute at any given time. But hopefully, the entire computation runs straight through without fault, because otherwise we have the synchronization point, which is very costly. And so I think you could say, well, how does this help us, right? It's not infrastructure ready. But I think the idea that the sort of way of thinking about the problem as this flyby could be made production ready. And then we already have a broadcast that allows the data to sort of flow across in this BitTorrent style, so we just intermingle that with the computation. And it would also save us this kind of funny business about broadcasting variables, because broadcast variables in Spark are sort of magical. Yes, we know how they work, but to Spark, they have to be kept around somewhere in case you ever unpersist them and then a partition needs to be recomputed, because otherwise they're simply not available. So they're stored in HDFS Scratch, but we already have the elements of the RDDs that were flying around. They're already in HDFS or hopefully written out, or if not, we have the provenance information and can recompute them. So as an experiment, I implemented a dense matrix class in Breeze. At the time, MLlib has one. I'll talk about that in a moment, but at the time it wasn't available. I have a cluster as part of my work. It has 5 nodes. They're quad socket, 8 cores, so 32 cores per node, 250 gigs of RAM each. This is Cloudera 5.3, so an older version of Spark, but I don't believe Cartesian has been updated since then, and Shuffle not seriously, not majorly. So I'm going to evaluate for n by n matrices, square matrices, for varying numbers of partitions, and this is a link to the code. It's available, but it'll be available on the next slide as well. So MLlib brought in a dense matrix library as of March of this year. And when I did this work, it wasn't available, so unfortunately I don't have a comparison for you, but I can say that the one I wrote is substantially identical to the dense matrix class in MLlib. And their matrix multiply, dense matrix multiply, is essentially the same as my Shuffle matrix multiply. So what we see when we actually do this is that Cartesian is the slowest, Shuffle is somewhere in the middle, and Flyby sort of, surprisingly, was much faster than Shuffle. I wasn't expecting that. We've tried this for varying numbers of, along the bottom, right? We have varying sizes of matrices that we're evaluating. So the first one is a 10,000 by 10,000 matrix. Now keep in mind, right, that's something that could be executed very fine on a small laptop using, NumPy. 25,000, that's getting to be a little bit trickier, and probably at the 35,000 or 30,000 level, I don't think either of those two would ever fit on a single node. So the numbers themselves, I can work this out by the predicted times that these algorithms should take, and what we see wall clockwise is satisfies what you'd expect for scaling. So I don't think I can explain this away by misconfiguration or things like that, other problems. I think it just really is the case that the Shuffle is kind of slow, and when you have predictable data dependencies, it's possible to do better. So what we saw here was that Flyby offered a significant improvement over the Cartesian, right? I mean, that's like the first column and the last column in each of these. Given that Flyby really was designed as kind of a drop-in for certain Cartesian operations where you have Cartesian map, it's combined by key, this is a great improvement. And for the application I was interested in, that matching application, this kind of saved the day. It made the wall clock time go from several days down to several hours. I think the improvement over the Shuffle multiply is a little bit trickier to make the case for. Obviously, the asymptotics are different. So at some point, Shuffle multiply would win. The question is, when do we enter the asymptotic regime? And I think as I talked through, the Flyby RDD would allow a lot of a lot of other tasks, if Flyby RDD, by which I mean something that's infrastructurized based on this, would allow a lot of algorithms that currently we can't support. So Gaussian elimination with partial pivoting, I think you can express in this Flyby format. Cholesky factorizations. Those are the two that I thought of off the, I don't want to say off the top, but with a little bit of work. And so there's finally the URL for the code. It's basically has no license, so you're all welcome to steal it and claim it as your own, whatever you want to do. It's right there. Please, I'd be glad to hear if you think it's helpful to you, or if you ever come across this problem, you can think of this and try it out. So with that, I think I have presented everything I have for you in a slide. I'd be glad to hear your questions. Thank you.
Okay.
Hi, very interesting talk. So there's a fourth approach that you could try, which is you could create a new RDD class where you introduce the dependencies to be exactly the ones that you want, right? So for example, you could create a new partition which exactly depends on the parent partitions that you want it to be dependent on.
So you're saying like a Cartesian RDD where each partition depends on n partitions of the parents.
Yeah. Because you do know the partition assignment, like you said before, and you can manually set up the exact parent partitions that are required for computing one partition of this RDD. How do you think that would compare? Have you tried that? Or?
I have not, no. My instinct is it wouldn't be any better than the Cartesian approach now, because those are all going to go through the cache manager, and that's essentially how the Cartesian approach works. We would possibly save this combine by key step to bring, let's back up here. Right. I did time this with a combine by key, which is a shuffle, which would bring those into the columns. I didn't break out the timings, but I suspect it wouldn't be a huge improvement.
Or to flip the question a little bit, so what is the greatest overhead in this Cartesian implementation? If is it the fact that your input read is extremely constrained because it's coming from one source to all of the different workers?
I think, yes. I think Cartesian could actually be optimized by, this is something I'm not sure about, but there's an order of execution that the driver has to schedule, right? And if there's contention for reading, right, if we have a bunch of RDDs all trying to get the one they depend on, right, this is going to be constrained, and the executor that holds this RDD will be overwhelmed in serving that, and it would probably result in a delay. I haven't got through to see if that's the issue and needs to be optimized away or not. It could well be.
Okay. Cool, thanks. Yeah.
Okay. We have one.
I'm curious what financial applications at Thomson Reuters has this been put to use in?
Sure. So it's matching, and it's based on, it's typically like suppliers and customers. I'm not sure I can disclose exactly who the suppliers and customers are, right? But we know things about the suppliers, we know things about the customers, and we want to suggest a way that those can be matched up. In the legal business, I might add.
Quick question. You mentioned Cholesky. Could this be used for a streaming application then, in terms of incremental updates?
Well, I think, yeah, for a streaming application, you would just be doing a series of broadcasts anyway, right, as the stream comes in. I'm not sure if the stream is time constrained. Maybe there's no need for it because the broadcast can happen in real time anyway.
Okay.
Yeah.
Okay, great. If there's additional questions, we can take offline. Thank you very much.
Thank you.